Okay, so we talk about some application of Bell-Manford algorithm. So we start with the so Bell-Manford algorithm can be applied to the area like how in the linear programming, solving the linear programming problem, but not the general linear programming problem. It has some which is called linear constant, how to solve the linear constant. So we will talk about that, and also we may discuss some of the other applications like how to detect a negative topological ordering of a graph. So those we may discuss. So let us start with the linear programming problem. So what is a linear programming problem? In short, it is called LPP. So what is a LPP problem? So LPP problem is basically we have some linear constant like say a11 x1 plus a12 x2 a1 in xn less than equal to b1 a21 x2 plus a22 x3 sorry a21 a2 x1. So these are the variable. So they are a2n xn less than equal to b2. So the ith term is a I2 x2 plus a in xn less than equal to bi dot 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 a in x1 or maybe m if there are if m1 if there are m such linear constant. So m1 x1 plus a m2 x2 plus dot 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 a mn xn less than equal to bm. Okay. So this is a given system of linear constant. Okay. Now this is this our x1 x2 xn must satisfy this, and it must maximize or minimize. There is some objective function maximize. It should maximize or minimize some function like c1 x1 plus c2 x2 cn. How many are there? Up to n, cn xn. So this function is called z, objective function. This is called objective function. Okay. So we have given system of constant like this, which is the basically the system of inequalities, and then we have to so which we have to find the xi x1 x2 xn which satisfy this system of constant, and then which will optimize this. I mean either the objective function could be in maximized form or minimized form. So which should optimize this. Okay. So this also can be written as the matrix form like ax less than equal to b, and this z also can be written as ct x, where A is the matrix A11, A12, A1n, A21, A22, A2n, AM1, AM2, AMN. Okay, and x is basically the vector x1, x2, xn, and b is also the column vector b1, b2, bn, and c is basically also the column vector c1, c2, cn. So this is the LPP problem in the matrix form. So we have to either, this is the objective function which need to be either maximize or minimize. Okay. So this linear programming problem, this is the general form of linear programming problem. So there are some algorithm to solve this linear programming problem. So one is simplex method, another one is some graphical method to solve the linear programming problem. So now here we are restricting our problem LPP problem to a very particular case where this each of this row is contain 2 element 1 minus 1. So, that means this A matrix, each row of the A matrix is, so each row of the A matrix is contain only 1 and minus 1, 1 1 and 1 minus 1. So, that means it will be like this. So, x 1 minus x 2 is less than equal to say 3, then x 2 minus x 3 is less than equal to minus 2, then x 1 minus x 3 less than equal to 2. Suppose this is our, so what is the corresponding matrix? Matrix is basically, so 1 minus 1 0, 0 1 minus 1, then 1 0 minus 1. So, x 1 x 2 x 3 and what is b? This is less than equal to, what is b? B is basically this 3 minus 2 2. So, that means each row is containing only 1 1 and another minus 1. So, the very special very particular case of LPP. So, these are called linear constant or difference constant. So, these are called difference constants. Okay. So, now we will just concentrate on this particular case or difference constant, how to solve the difference constant. So, this we will just look at how to solve the difference constant, and then we have, after getting the solution, we have some optimization function maximizing or minimizing some objective function there. So, that will be we'll discuss. Now, can you give me the solution for this function for this constant, difference constant? So, any value of x 1 x 2 x 3 which can solve this? Will you apply the simplex method or just by looking at this, or some graphical method also you can apply? But anyway, if we just try it, I think the solution will be x 1 equal to 3, x 2 equal to 0 and x 3 is equal to 2. So, one can verify if we just put it, it is satisfying all this. So, it is satisfying all this. This is the solution for this difference constant system. Okay. So, now we want to see how the Bellman-Ford algorithm can help us to get the solution of such different constant, and how we can make use of Bellman-Ford to have the solution of this thing. Now, for Bellman-Ford we need a graph. Now, we need a directed graph. Now, the question is how to construct a graph out of it. So, how to construct a graph from the given different constant, I mean system of different constant. Okay. So, to construct a graph, suppose we have a node like, we have a different we have an equation like this, xj minus xi is less than equal to wij. Okay. So, this will correspond to a part of the graph like vi, or you can just say xi also. This is just a notation, I mean notation of denoting the vertex. So, this is basically wij. Okay. This is basically wij. So, xi, if this is a constant, this is called constant graph, constant graph. So, given a difference constant, we have this corresponding graph. So, what is the graph corresponding this? What is the constant graph corresponding this? So, from this we have what? So, this is basically x1, or x1 we can denote by v1, v2, then we have v3. So, we have x1 minus x2 is less than equal to 3. So, that means, so this is basically this is x1. So, wij, so this is basically x2 minus x1. So, this is 3 and then x3 to x2. So, x3 to x2 we have a minus 2 and then x3 to x1 we have plus 2. So, this is the graph, this is the constant graph corresponding to this difference constant, this system of different constant. Okay. So, we have the graph. Now, once we have a graph, this is a directed graph with the edge weight, and this edge weight could be negative also, because Bell-Manford can handle the negative cycle. So, there is no restriction on the negative weight edge. Okay. Now, given this graph, we have to do, so what is the, so now once we have the graph, we can apply the Bell-Manford algorithm. So, we can apply the Bell-Manford on this. Bell-Manford we can apply. So, once we apply the Bell-Manford, it will give us the, either it will report a negative cycle or it will give us the shortest path weight. Okay. Now, suppose it is giving us a negative cycle. So, that means there is a negative cycle in the corresponding graph. Then we have to show that the solution, there will be no solution of the system of constant. So, that means system of constant is infeasible. So, so this is called infeasible or unsatisfiable constant. So, what it is telling? It is telling that, so this is a theorem, if the constant graph contain a negative cycle, and that can be determined by Bell-Manford, contains a negative cycle, negative weight cycle, then the system is infeasible, then the system is not having the solution, then the system is unsatisfiable, that means there is no solution. Okay. So, how to detect that whether there is a negative cycle? So, we convert this system to a graph, constant graph, then we run the Bell-Manford. So, once we run the Bell-Manford, we can easily see that whether there is a negative cycle or not, because Bell-Manford will report the negative cycle if there is. So, then if Bell-Manford is reporting negative cycle, then there is no solution exists for this system. So, how to prove this? So, how to prove this? Okay. Okay. So, to prove this, suppose there is a negative cycle in the graph. Suppose that the negative cycle, suppose this is a negative cycle in the graph V1, V2, V3 dot dot dot, it will reach to again V1 is a negative cycle. Okay. Suppose this is a negative cycle. Now, in the graph, in the constant graph. So, now, so this is basically, so from this, what is the corresponding constant we have? So, from this we have the constant like x2 minus x1 is less. So, this is basically W12. So, W23, and this is basically W if this is Vk. Okay. So, Vk2 again V1. So, W this weight is W K1. Okay. So, now comma. So, this will be corresponding to x2 minus x1 is less than equal to W12, and this will corresponding to x3 minus x2 is less than equal to W23 like this, and dot 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 xk minus xk minus xk minus 1 is less than equal to W k minus 1 comma k, and then the last one is x1 minus xk is less than equal to W k comma 1. Okay. This is coming from this graph. Now, if we add it up, so this thing will cancel out, this. So, this part is 0, and this part is basically sum of these weights, and sum of this weight means weight of the cycle. So, this is basically weight of the cycle. Now, this is a negative cycle. So, this weight is negative, this is less than 0. So, this is the contradiction. So, that means we are not having a solution for this system of constant. If we have a solution, then we should not reach to this contradiction. So, this is, so we are not getting a solution. So, that means there is no values of xi can satisfy this constant, because this is 0 and this is negative, which is not possible. So, there is no values of xi which can satisfy this constant. So, this is the proof. This is the proof by contradiction. So, there is no values of xi, no values of xi which can satisfy the constant, which can satisfy the constant. Which can satisfy the constant. So, this is the proof. Okay. So, that means if there is a negative cycle in the graph, then that will then there will be no solution will exist. So, that means then there will be no, then the system of constant is not feasible, it is a unsatisfiable. Okay. So, now we have to prove the other way around. Suppose there is no negative cycle. So, that means Bell-Manford will give us the solution, Bell-Manford will give us the single source shortest path. Then from there, how we can get the solution for this constant, how we can get the solution for this system of equation. So, that we have to show in the next. So, that is the satisfying of the constant. So, if there is a negative cycle in the graph, then this system of constants, different constants are not feasible. That means it is there is no such xi which satisfy this. Okay. So, let us just write this. This is the feasibility condition, feasibility case, or satisfying the constant. So, here there is no negative cycle. So, that means we have a solution. So, suppose, so this theorem is telling, suppose no negative cycle in the graph exists in the constant graph, then the system is feasible. Then the constant are satisfiable or feasible, then there is solution for this constant. Then constants are satisfiable. Okay, so this is a case where we have the solution for this system. So when there is no negative cycle, we can expect the solution. So how to prove this? So to prove this, we just do some we just add some vertex in the graph. So what we do? We just add a new vertex. So what we have? We have a system of constant. From there we construct the graph, constant graph, and in that constant graph, what we are doing? We are adding a new vertex. So just adding. So add a new vertex. So that will be a starting vertex, a source vertex, because Bellman-Ford needs a source vertex. This is a single source shortest path algorithm. Add a new vertex S to V. V is the constant graph. V is the constant graph, which is coming from this constant, different constant. Vertex V. And add the edges from V to any other vertices, and add edges from S to all other vertices. Vertices with edge weight 0. Edge with edge weight 0. So that means W of S comma V is 0 for all V. So these are the, so from S we add the, so V1, V2, V3 we add the vertices to all other edges to all other vertices. Okay. So let us just draw that graph. So basically we have the constant graph, say like we have some vertex V1, V2, V3, V4, V5, and we have the they are connected. So depending on the constants, they are connected somehow. Suppose this is, now what we are doing? So this is a constant graph coming from that difference constant. We are adding a vertex, and we are from this vertex we are adding the edges to all other vertices. Okay. And this we are adding weight to be 0 to this newly added edges, and this is for all other vertices. So this is the way. Okay. Now if the original graph is having no negative cycle, so that means this new graph just adding a vertex S will not having a negative cycle also, because we have just added the 0 weight edge. So 0 weight edge, by adding 0 weight edge, it cannot make the negative cycle, because the original graph is having no negative cycle. So though no negative cycle in this graph. Okay. So if there is no negative cycle, we do the Bellman-Ford algorithm and we run the Bellman-Ford algorithm. So no negative cycle means shortest path exists. Shortest path exists. Okay. And so that means we will getting delta of S comma Vi for all Vi belongs to V. So this we are getting. So we are getting delta of S comma Vi for all Vi belongs to this. Okay. So now this we are assigning to, so this exists because there is no negative cycle. So Bellman-Ford will give the solution, so this exists. So this we will define as Xi. Okay. Now what we have? We have this, say Vi and Vj and we have this S vertex over here. So, from Vi to Vj, what is the weight? Weight is Wij, and so that this is from Vi to Vj. Yeah, Vi to Vj, weight is Wij. So, now we have a delta of S comma Vi due to Bellman-Ford, and this is delta of S comma Vj. Okay. So, now by triangular inequality, what we can say? We can say this delta of S comma Vj, this is basically the weight of the shortest form from S to Vj, and this is one of the paths. So, this must be less than equal to delta of S comma Vi plus Wij. Okay, delta of S comma Vi plus Wij. Now, we can take this side. So, delta of S comma Vj minus delta of S comma Vi is less than equal to Wij. These are the solutions. So, this is the system of constant. This is that ith constant. So, and this is the solution. So, if we just assign this to be xi and this to be xj, so that means xj minus xi is less than equal to Wij. So, these are basically, these deltas are basically solution of this constant. So, these deltas, delta of S comma Vi, these are the basically gives the solution of the constants. So, these deltas are giving the solution of the constant. So, what we are doing? We are having a constant graph, we are just adding a vertex S and we are adding the edges with 0 weight with the 0 weight. Then we run the Bellman-Ford, and since there is no negative cycle in the original graph, so there will be no negative cycle in this new graph. After running the Bellman-Ford, so we will get the deltas, because the shortest path will exist, and these deltas are nothing but the solution of this constant that is coming from this triangular inequality. This is the triangular inequality. So, this is coming from this result, and this is the constant, and this is satisfying this constant. These deltas are basically satisfying this constant, and so these deltas are basically the solution of the difference constant. Thank you.